I'm guaranteed to give you what you need.
Check this out!
Hey, this is Ed Lee, and I'm here to tutor y'all in physics. This is the first lesson having to do with scalars and vectors, usually the very first thing that's taught in an introductory physics class, so let's get started. Today, let's take a look right here. We see that we have scalars over here, which is measurements that are made for magnitude only. And vectors are their magnitude, but they also contain some element of direction as well. So let's take a look at some examples. Some measurements that are measured for scalar quantities would be something such as meters, distance, length. They only have a magnitude. Mass only has a magnitude. Temperature only has a magnitude. Let's take a look at some things that would be vectors. That would be something such as force, acceleration, momentum. Those kinds of directional forces that we think of, and it's kind of intuitive when we think about it. So let's come up with an example right now. So let's suppose that I am going to just just expand in size, right? I'm going to grow, become more massive. Now, massive is a function between density and volume, so if I just say I'm growing, right, that means my volume is increasing, right? Volume is also a scalar or a vector. It's a scalar, right? If my volume increases, right, I'm just growing to the sides, growing in front, growing in back, I'm just growing, right? Hopefully in my videos as I work out, you'll see me getting larger volume. That would be cool. But the vector quantity, right, it's not a vector quantity, volume expansion, because if I can't really grow in one direction. However, force, if I apply force in one direction, I'm coming at you like that, then I am applying that in one direction, right at you. So that's the difference between a vector and a scalar, right? A scalar can't really be directed into one pathway. So the thing is that why do we divide things up into scalar and vectors? Because the way that scalars and vectors interact with each other is a little bit different. Scalars are very easy to work with because they're just pure magnitude. So if I have something like a distance, right? Like if I take something from my elbow to my shoulder over here, right? That would be a certain distance. And I just add the distance from my shoulder to my other shoulder. I could have a combination of this particular length right here. That's very easy. That's a scalar quantity. I could also take something like volume. I have 1 cup of volume over here, right? And then I add another cup over here. And then I have, very easy calculation. I just add those two together. But vectors add a new component. They add direction. So what happens if we multiply a vector by a scalar quantity? Well, one of the most famous rules in physics, which is force equals mass times acceleration, uses exactly this principle. Mass, which would be a vector or scalar, mass would be a scalar quantity, right? And you multiply it by acceleration, right? Acceleration is applied in one direction. You could accelerate or have your velocity increase in this direction. You can have your velocity increase in that direction, right? So velocity is a scalar quantity that contains a directional component to it, as well as a magnitude component. You multiply those two together and you have force, right? And force can be applied in one direction, right? You're applying a force to this object, causing it to move, right? And we have a scalar quantity. What happens if we try to combine scalar quantities? This is where our trigonometry comes in. So over here, you can see that we have before we cover the idea of trigonometry, we have to cover some real basic concepts. You should have this down, but if you don't, a short review. Okay, here we can see that we have a circle right here, and we can see that it's been divided into 4, right? Now, if I do something called a 360-degree rotation, right? I could take this pen over here, right, and I do a 360-degree rotation, right? That would be a full 360-degree rotation. If I just turn it, I'll also do it in a way that's going to be easy for you to see, like this. This would be a full 360-degree rotation, right? Pointing up to like 12 o'clock, right? Full 360-degree rotation, right? Back to 12 o'clock, right? If I do a 90-degree rotation, it would be right there, right? To 3 o'clock, right? Like that. Or I could do a 180-degree rotation just like this, right? that's 180 degrees. So sometimes you'll see like extreme sports athletes that do like a lot of spinning, things like that, skateboarding, snowboarding, you know, they do tricks where they might spin, you know, for a full turn, and that would be like a 360-degree turn, right? So, or a 180, right, where they just go like this, and then they are spinning, and then they're just facing the opposite direction where they took off from, and that would be a 180-degree spin. So, why are we talking about angles? Because when we look at triangles like this one over here, right, any triangle has a certain functional identity where the sum of the angles, right, we take like this angle here, there's an angle here, there's an angle here, right, the sum of these three angles, no matter what triangle it is, will always equal 180 degrees. But we have a special case because in this case, this is a right angle triangle, right, which means that one of the angles is 90 degrees. That means that one of the angles here, we'll call it theta. This is a Greek symbol, right? Why do we use all these Greek symbols in physics? Because we come from a Western school of thought, and Western, you know, according to Western educational system, we learn from the Greeks and the Romans, so we have a lot of Greek and Roman letters within our alphabet. You know, we also have a lot of contribution from the Arabics, but we don't really give as much, you know, credit to them. You know, Chinese people invented a lot of math stuff, but you know, that's alright. You know, I'm coming from Western style education myself, and they made a lot of contributions, so they earned it to a certain extent. But I just don't want to, you know, leave out my Arabic and, you know, Eastern brothers for their contributions, but whoosh, that's another story and not about this. Let's just get to what you're going to have to learn for physics. So here we have theta, right, which means a variable, right, just like we use x a lot for algebra, we use theta for angles, right, and then this would be 90 minus theta. So if this is 30, this would be 60. If this is 45, this would be 45. If this is 27, then this would be what? 63, right? 63 plus 27 is 90. Yeah. So just that kind of functional identity is going on. This one over here, this angle right here, right? The longest side is called the hypotenuse, right? This is called the hypotenuse. It's just another name you're going to have to memorize. This one over here is adjacent. Adjacent means next to it. But it can't be this, even though it's adjacent to this one and adjacent to this one, we can't call this one the adjacent because we already gave that a name. It's called the hypotenuse. So this one is the adjacent, and this one is the opposite. You can see it's facing the opposite side, right? So when we see our sine, cosine, tangent over here, we see that we have sine, right, which is the opposite over the hypotenuse, cosine, which is the adjacent over the hypotenuse. So it's kind of easy to remember because sine and cosine kind of sound alike, and we can see that they're both over the hypotenuse, whereas tangent is a completely different sounding name, and it's the opposite over the adjacent. So these relationships are going to be having some kind of scaling quantity or some kind of proportional quantity. So the thing is that we take a look at over here. Now this is actually one of the most famous triangles that you're going to see. Is the 30, 60, 90 degree triangle. In this case, theta is representing 30 degrees. And this one over here is representing 60 degrees. Okay? And the proportions would be 1, 2, and the square root of 3. Right? If we're using certain units, right, like meters or inches, you might have to multiply this through a certain number. 2.5 multiplies by 2.5 multiplies by 2.5, but this proportionality constant will always stay the same. So this will come in handy later on when we have, for example, a force component. Let's suppose that we have 2 newtons of force being applied in this direction right here, right? 2 newtons of force coming downwards into, you know, let's say there's a comet that's applying 2 newtons of force that collides with the Earth and applying 2 newtons of force. It would be much more in reality, right? A newton is a very small amount of force, but we'll just make it real simple because we have the numbers right here. 2 newtons of force, right? So the amount of vertical component of the force would be only 1 newton, whereas the horizontal component of force would be square root of 3. So a square root of 3 is actually larger than the 1, but smaller than 2. So if we have you know, some kind of a uniform type of substance here that the comet is colliding into, then it will actually go further this way than it will go down this way, which kind of makes sense because you kind of see it making this path. So Physics can be intuitive. You just have to relax, take a deep breath, and just look at enough problems, and it's going to make a lot of sense. It's not that hard. So what happens is that if you have this 2 over here, right, that number might not be a 2. It might be a 200, right? 200. So how would you, and then they might ask you, for example, what would that be? So easily you could just say, oh, well, it's 100, right? 2 is to 200 as 1 is to 100. But if it was some weird number like 54.6 or something like that, right? And actually that's still not that hard because you just divide by 2 if you're good with numbers, but let's suppose that you're not. So 54.6 would be this component or the hypotenuse. So if I'm trying to find this one, right, and I know that this angle is 30 degrees, right? 30 degrees, and this is going to be a setup for a lot of problems that come up later on. This is 30 degrees right here. You have 54.6 newtons of force coming in like this. How much vertical component force is entering at this point right here? Let's find out. 54.6, which is going to be the hypotenuse, multiplied by, right, the opposite over the hypotenuse, which would be the sine over here, right? The sine. If you multiply that, the hypotenuse will cancel out, and then you'll be left with this component over here. So because of that relationship, 54.6, right, you can see that 54.6 is divided by 2 is going to be what? 27.3, right? And you could just do that on your calculator at home. On the MCAT, you're not allowed to use a calculator, so if you're studying for the MCAT, you better start getting good with doing math. I recommend that you do it on a piece of paper and pen. Why make silly mistakes? Watch, I'm going to make a mistake later on. I'll be smacking myself. Losing points that I didn't need to lose. But this is just something that for you to know about. So this is why for scalars, right, you have different components coming in and you need to do these calculations. So if you have any questions or comments, please put them in the section below. And, of course, like and subscribe and tell your friends. This is totally free, and I hope you guys enjoy. Next lesson coming right up.